Hello everyone. We are going to start with the quick review, and this review kind of covers most of chapter 7 um, because we are finishing it and I wanted to go over one last time. But it is chapter 8 is very related to this, so we are going to see similar terms, similar equations in the next chapter as well. So the first equation is the conservation of energy. Okay, so this is going to be very important for next chapter, and in this chapter we start learning each quantity in this equation kind of in detail, but not all of them yet. Okay, so we start with the kinetic energy. It is the K in the equation, and it is given as 1/2 mv squared, so it depends on the mass and the speed of the object, not really the velocity. So the direction does not matter, okay, for the kinetic energy, because energy is scalar, right? Does not have a direction. So if there's a change in speed, so then you will have a change in kinetic energy. So you're really focusing on the speed to check if delta k is 0 or not. If there's no change in speed, it was 0 initial, final also 0, then you're gonna say that delta k goes to 0, for example. For potential energy, the important thing is the elevation, okay? And that is represented by y in the equation. So mgy is our potential energy. Mg is the weight force, right? So the weight force times the elevation gives you the potential energy of the object. So it's kind of, with the elevation, it has more potential to fall down, and it has more energy to convert it to more speed, for example. So one thing is, which is very important, and you have to show this in the problems, specifically for the U term in the energy conservation, you need to show your y-axis. Okay, it's always y, it's always vertically upward, and we always look at the bottom point and make that point to be 0 potential. So you need to assign the initial potential or final potential. So I usually go with the bottom and then set that to 0, so I don't have to deal with negative potential. But it can be negative as well. It's relative to where you choose to be y equal to 0. Okay, so again, we will solve more problems in next chapter. We will start with potential energy in more detail, but these are some basics for now. So if there's a change in elevation, you may want to keep the change in potential energy delta U term in the equation. But we also saw that the work term on the right side in the energy conservation has several terms depending on the free body diagram, how many forces you have, that many work terms you may have, some of which might be 0, but you need to kind of show that out. And one of them is usually the weight force, right? Almost all the time we have the weight force. So although there might be an elevation change, you may not want to keep delta U in the equation. So you can say that, okay, I'm gonna ignore delta U, I'm gonna keep the weight force work done on the right side, on the energy conservation. Okay, so we have a choice and we have to be careful with this. I cannot use both of them. I need to choose one of them. And again, please look at some of the problems we solved so far, and we are going to solve more, and try to really absorb this, because this is one of the tricky things, that choice that we have to make between delta U and the work done by the weight force. Okay, so they both are related to the elevation change, and you are going to choose one of them when you are applying the energy conservation, and say, I'm gonna maybe choose delta U and I'm gonna ignore the work done by weight force, or I'm gonna ignore delta U and I'm gonna keep the work done by the weight force. Be careful with that one, okay? And next step was calculating work. So first we looked at the plots on a force versus distance or displacement graph, we looked at the area under the curve, right? And that gave us the work done by that force along that displacement direction. It could be x, y, z, whatever the axis given. And we realized that it could be positive or negative or zero. So work has a sign, but work is also scalar. All those terms are scalar in the energy conservation equation. Okay, and again, work can be negative. That doesn't mean that it has a direction, though. It just means it's if you're putting a work term as negative, that means that force is doing a negative work, so it's really stealing the energy from the system. If it's positive, that means it's adding the energy into the system. Okay, so on a graph, so that's how we deal with it. But for the energy conservation equation, we need to, most of the time, we need to figure out what the work done by a specific force. So first thing you need to ask yourself is, are you dealing with constant force or a variable force? If it is constant, it's simply F dot D, and F and D are bolded because they are vectors. I just want to highlight that. I'm putting arrows on top. They don't really look like arrows, so arrows on top, and that becomes FD in magnitude and multiplied cosine theta. And the theta is the angle between F and D. I usually start those two vectors from the same point in my mind and then look at the angle between them, and that's what theta is. And again, cosine theta is related to the sign of the work. It could be positive or negative, or could be zero. If theta, for example, is 90 degrees, the work term becomes zero, although you have displacement and you have force. Okay, so that is the calculation part. If we have variable forces and we don't really know what sort of variable forces, like spring force is one example, but we don't know in general the forces given in terms of maybe x, y, or z functions, or multiple of those are used in the function. Then we would look into like how many dimensions we have, and we did a couple examples using one-dimensional case, and we just chose the first term because it was along the x direction. But what we needed to do was to take the integral. Okay, and again, think about if fx and dx points the same direction, so displacement and the force direction. If they're opposite, you take negative. If they're the same direction, the work done will be positive. Okay, and again, you kind of go through the integral most of the time, and this is the spring work done by the spring force equation is how we got it, right? We did that integral and realized that it is initial minus final for the work term. Okay, in the next chapter, we are going to look into the potential energy term. It's going to be different than mgy. We will call this potential energy mgy as the gravitational potential energy, and the spring one is going to be the elastic one. So there will be multiple potential energy terms. And later we did the power. So power is, I really want you to think this in terms of the rate of energy per time. Okay, so it's really what it is. So it's not energy per time. It is not just energy, it's the rate of energy. It is per time. Okay, so it's like energy divided by time. And instead of energy, it's really the real definition we said was rate of the rate at which work is done by a force. But what is work done by a force? It is a way to add or take energy, right, in or from the system. So it's basically, it's really, this word is important, rate of energy, and that's what power is. So since it is energy per time or work per time, the units of power is watts. So 1 watt is 1 joules. That's the energy term per seconds. Okay, that's the unit. And again, you can use another actually unit, commonly used unit for power is horsepower. So you can also convert horsepowers to watt or vice versa. Average power, just like the terms that we discussed earlier, average, like we start from average displacement and so average velocity and average acceleration, and then we said those were the vectors. Now we're saying average power, and power is not a vector either because it's energy per time. Neither energy nor time are the vectors, and power is also scalar. Okay, and average power, as we did before for average velocity and acceleration, we put a bar on top, right? That's how we represent it. And that is the work done divided by some certain time interval. So it's finite time. And again, work is energy per time. Okay, that's how we get the average power. An instantaneous one, we drop that bar. It's just P, capital P, and we take the limit and we made that delta t very, very small, infinitesimally small, right? The delta t goes to 0, and that would give you the derivative dw over dt. And we did an example last time where we had to use a variable force, calculate the work done using the integral as we shown earlier, and then you kind of need also to take the derivative to figure out power. And one other thing is power is also, we shown that too, f dot v, which means f v cosine theta, but the assumption for that is f is constant. If it is not, you cannot use that. So you can also find the power this way as long as you know that force is constant. Okay, and that's really overall what we've seen. Hopefully this helps you, because this is the end of the chapter, but we are starting chapter 8, but these are going to be still very important concepts to carry and build on top for the next chapter.